Bismillahirrahmanirrahim. Assalamu alaikum. Dear student, let's start lanthanides and actinides. So first start from lanthanides. So for lanthanides, you already know that they are represented by the general symbol of Ln. They are called inner transition. We have already discussed that why they are inner, because the orbital which is involved in bonding is inside the atomic structure. Therefore, they are called inner transition. But in more detail, we have to define these elements in further discussion, inshallah. So generally, they are represented by electronic configuration as given on the screen. N electron can accommodate maximum 2 electrons, n minus 1 d can accommodate maximum 1 electron, and there should be 1 to 14 electron in n minus 2 f orbital. Now, lanthanides, why they are called lanthanides? So, technically, we can justify the statement that since the electronic configuration of lanthanide series and lanthanum in terms of penultimate shell is similar, therefore they are called lanthanides. In other words, we can say that the valence shell, not valence shell, but penultimate shell electronic configuration of lanthanides and lanthanum is similar. Therefore, the series is called lanthanide series. Now, simply we can also say that since the series follow lanthanum, therefore they are called lanthanides. Uh, uh, why they are called F block elements? So the last electron enters into F subshell, therefore they are called F block elements. Or we can also say that since F orbital is under the process of completion, but this definition is limited because of certain reasons at the end of the series where F orbital is not incompletely filled. So those elements where F orbital is under the process of completion, so they are called F block elements. And logically, whenever an orbit is under the process of completion, so the end also comes, and that end is at the extreme of the series. There are two elements which have F14 electronic configuration, so they can also be included in the series according to this definition. But the most broader definition is the one where the last electron enters into the F subshell. So this, I will suggest that this is the most diversified or most wider definition for F block elements. These elements are sometimes also called rare earth metals, and this rare earth metal name is given to the series because of their concentration in the earth crust. Since they are rarely occurring elements in the earth crust, therefore they are called rare earth metals. But this rare earth definition, the name rare earth metal also is limited because of the reason that there are certain elements which are lesser in concentration than lanthanides, but they are still not rare earths. And F block elements in some books they have been called as rare earth metals, but really they are not rare earth metals. And inshallah, in coming slides, we will come to know that why they are no more rare earth metals. Now coming toward electronic configuration, you already know about electronic configuration of lanthanides. In this slide, let's focus on the yellow portion of the diagram. So first electron enters into 1s, then 2s, then 2p, 3s, and accordingly the electronic configuration will follow the electronic configuration rules. So coming to 5p, where 6 electrons have been accommodated, these total electrons are 54. At this side, you can see that there are noble gases starting from helium through radon. So xenon is 54. The electronic configuration of xenon are total 54 electrons have been represented by these yellow color balls or circles. So for our easy discussion in next slides, we will represent these electrons by xenon in the in square brackets, which will we call closed shell electronic configuration, and definitely for xenon, but this is closed shell electronic configuration. Below this limit, the reactivity cannot be extended. Above this limit, reactivity will start, so we have to discuss reactivity of lanthanides above this limit, not below this limit. Now other electrons will enter into 6s 5d or this 4f orbital, and generally the electronic configuration of lanthanide can be represented by this electronic configuration, this that xenon electronic configuration, and beyond xenon there will be two electrons in 6s and one electron in 5d. Electron can occupy 5d or can occupy 4f uh, because they are too close to each other, but in order to justify the chemical reactivity of lanthanum, this electron has been accommodated by D, not F, and that is why lanthanum is uh, out of the series. That is not F block elements, but that is D block elements. So this is electronic configuration of lanthanum. So we have to put closed shell electrons, closed shell electronic configuration in the square bracket, and this closed shell electronic configuration resembles xenon. Therefore we have to put xenon inside the square brackets, and beyond 54 we have to represent electrons. So the lanthanum will have two electrons in 6s and one electron in 5d subshell. Now let's draw electronic configuration of the series. So starting from lanthanum, we will include lanthanum in the series because the penultimate shell electronic configuration is similar as lanthanides have. Therefore, the lanthanum has also be included in the series. So it makes the total number of elements in the series 15, not 14. But actually, the lanthanide starts from cerium to lutetium, not from lanthanum. So starting from this electronic configuration, as we already discussed, there was one electron in D and one electron in S. And since we are discussing F block elements, so logically their next coming electron should enters into F. So according to rules, then coming electron enters into F, which makes cerium as F block element. So starting from F1, and this electronic configuration actually violates general electronic configuration rules. That is why it has been marked as red. That 5D also accommodates one electron. So this is an anomaly. This is a violation which cannot be explained by following general rules of electronic configuration. So starting from electronic configuration of lanthanum cerium, which is 4f1. So then the next electron enters into 4f, 4f, while the 5d also remains empty, so there is no f2 system, while the system is then next is f3, 4, 5, 6, and then there are 7, which are two systems. And why they are two? Because the 4f7 is half filled, and in this case, in case of gadolinium, also general electronic configuration rules are violated in order to attain extra stability. And the next electron which will make this system is 4f8, which we expect according to rules. That eighth electron will enter into 5d, leaving this 4f half filled in order to attain the required stability. Then 8 is missing, so 9, 10, 11, 12, 13, and 14 is logical completion of the series in terms of electrons in F subshell, and another shell is also for a 14, and now the next electron will enter into 5d, which follows normal electronic configuration group. There is no confusion. So in the series throughout, if we analyze it, so there are two violations for gadolinium and cerium, where the end So we'll come back. We were discussing electronic configuration of lanthanides, and we discussed that there are violations in case of cerium and gadolinium. So this one we were able to explain that why gadolinium violate the rule, and in case of cerium, normal rules cannot explain this violation. Let's summarize or uh, decompose this table. And there are three portions which are of prime importance. So one is on start or in the beginning, which is 4F0 system for lanthanum, and this is empty system. These two systems are half filled. So in case of this system, we can explain why rules have been violated, because 4F7 is relatively stable as compared to 4F8. Therefore, the system adopts 4F7 electronic configuration, not 4F8. And at the end, there are two systems which are 4F14, which are completely filled, and again they are stable. So, on the basis of these stable electronic configurations, the violation, if any, can be explained. Now, let the table. There are certain points of interest in the table. There are two violations which have been marked red. There are some systems which stable electronic configuration, and these stable electronic configuration will further be utilized in chemical reactivity and physical reactivity of lanthanides and actinides. So once again, F0, F7 and F14 systems are stable, and if electrons violate rules in that region, then you could be able to explain the violation of electrons in those particular regions. Next is why the F block elements are called F block elements, or what will be the logical definition of F block elements. So F block elements are those elements in which the last electron enters into anti-penultimate energy level, and for this electron, the elementary or ionic state is condition that the element can be in neutral state or can be any of its ionic state, and if one last electron enters into F anti-penultimate subshell, then the system will be called as F block element. The element will be called as F block element. Then what is anti-penultimate shell? Consider this is a structure of an atom. In the center is nucleus, and besides the nucleus, outside the nucleus, there are shells. So there are three shells have been shown for simplicity reasons, and three have been omitted for clarity or simplicity in order to make things understandable. This is four shell, fifth shell and sixth shell. So the last one, which is the most outer shell, this is called ultimate shell, and it is represented by NS. The next one which comes underneath is second last, and this second last by nomenclature is called penultimate shell subshell, and this penultimate subshell is generally represented by n minus 1t, because this one is 6 and 6 minus 1 makes 5, so this is the fifth one. And third last is called anti-penultimate subshell, which is represented by n minus 2f. So 4 is, if we represent n by, if we put n is 6, so 6 minus 2 is equal to 4. So this is anti-penultimate subshell. So according to definition, the coming electron enters into 4f shell, which is called anti-penultimate subshell. So if incoming electrons